off of where we were for step 4. So we're on. Oh, sorry. Let me close this here, and then let's open up where we last left for step 4. Come on. Okay. So yeah, step 4 here, differentiate the equation from the previous step with respect to time. That's what we have. We can rewrite this just so it looks a little bit, I don't know, more familiar to you. So it's 2 pi r times dr over dt, and we're going to carry that over to step 5. Right? Where step 5 indicates that we want to substitute in the values and solve for the unknown rate of change. So step 5, let's bring in that equation that we had in the step 4. The rate of change of area, or the dA of dt, is equal to 2 pi r times what is it? The derivative of r with respect to t. Let's just substitute in some values here. We know that we're talking about we're trying to solve for the dA of dt at the point where the radius of the puddle has expanded to about 25 feet. Okay. So we're going to substitute in the radius for 25 feet. So 2 pi times 25 feet. And then we're going to multiply that to the rate of change of dr, or the rate of change of the radius. And we knew the radius constantly changes at a rate of 5 feet per second. So let's write that in with the units. 5 feet per second. Let's multiply that out. I'm going to leave the pi as a constant. So what is a constant representative marker or symbol? It's just pi. I'm not going to actually integrate 3.14. Then we're going to do 2 times 25 times 5. So 2 times 25 is 50. Times 5 is about 250 pi, and it's feet times feet. That's feet squared over seconds. And then how you can kind of check that you did it right, does the rate of change for the area, do the units make sense? Well, we're talking about how the area, which is in feet squared, changes over time, over seconds. That looks to be pretty good. Okay, so that's how you do number 1. Why don't you try number 2 on your own? Right here on the left hand side. Okay, read that to yourself for just a second, or pause it, and I'm going to set my page for that problem. Okay, so let's go ahead and begin. Let A be the area of a square whose sides have a length. So we're talking about area. So we got area. Let's keep that in mind, of a square whose sides have a length s, and s varies with time. Okay, so s varies. That means s changes with time. That's a rate of change of s. So we know that we got ds over dt. Then we got just the length s. And we also have area. Okay. At a certain instant, so when they talk about like at one point, okay, the sides are 3 feet long and increasing at a rate of 2 feet per minute. Okay, so it looks like I got this s is going to be equal to 3 feet and increasing at a rate. So ds over dt, how the rate increases at one point or at one instant, will be 2 feet per minute. What is it? So how fast is the area increasing? So it looks like I'm looking at how, not just the area, but how it's increasing. So that means dA over dt. Okay, so got a lot of little things here to kind of take note of. Let's go back to step one. Let's just start with the basics. Just the variables. Let's think of just the variables. Well, I know I got A for the area of a square, which they don't give you anything. Okay. Then they got S, which is the side of the square. And everything is in regards to t. So it seems like everything is like a function of t. Whatever the time is, the side is going to change and the area is going to change. But t is whatever time you want to put in. Okay, so t is going to be the time. We're looking at time in minutes. Sides, I think, are in feet. And then area, that'd make it feet squared. Okay. And it does look like we're looking at when the side is 3 feet. So S is going to be equal to 3 foot at some point. Then we look at step 2. Let's look at rates of change. So let's see here. The rate of change of, let's see, S varies with time. It says right there, at a certain instant, and we're looking at an increase of rate of, the sides are increasing at a rate of 2 feet per minute. So that means side, we're looking at how side changes, ds over dt. And if you want, you can actually write down like what that is. That's like a, let's see, sides rate of change. The sides is rate of change. We're looking at an instant where that rate of change happens to be 2 foot per minute. 2 feet per minute. We're also looking at how fast the area, that's actually what we're solving for, because it asks how fast is the area increasing at that moment. So we're looking at the rate of change of the area. Rate of change of the area. And at the particular moment when the rate of change of the sides is 2 feet per minute and when the side of the square is 3 feet, okay, what is the rate of change of the area? That's what we're trying to solve for, right? Okay, and step 3 is to draw the scenario. So again, we have A is the area of a square whose length has length S, and then it's actually growing. So it looks like, so here we have a square with an area of A and side lengths of S, and it's slowly expanding, right, to a bigger square. So let's see, it'd be like, I don't know, I'm trying to get it just right. We're trying to stop it at the point where the side length is 3 feet long. So that's for the sides. And the rate at which it's increasing, the ds over dt, is 2 feet per minute, per 1 minute. Okay. Then we're asking, just as a whole, how big is the, or how fast is the rate of the area changing in that instant where the rate is 2 feet per minute, the side of, and the actual side lengths of each of the squares is 3 feet. Okay, so that's step 3. You don't have to draw it, but it helps. Oh, and let's make it a relationship. Okay, so it's best to start with nothing with derivatives. Let's just say area of the square is literally equal to what? In terms of the length being S. It'd be S times S, right? Which would be S equals A is equal to S squared. And we want to include, like, actually, that's about it. We're just going to leave it like that. If you must know, we're going to take the derivative of both sides. So that's kind of where you want to end up. You don't have to have that just yet, but to leave it like that. And then step 4, let's go ahead and take that and differentiate it, because we are including time by saying that we're taking the derivative of the area and s with regards to t being the independent variable that you input. Like you put in t is equal to 1 second. If you do that, it changes the area and it changes the sides. If you change it to 2 seconds, then the area is going to be different, because you know at 2 seconds it's going to be growing out. It's going to be at a different point, and the side lengths are going to be longer and longer and longer and longer as you put in a higher time. Okay. So now let's go ahead and take this and differentiate it. On one side you got dA over dt, and then you take the derivative of s squared with regards to s to the second power. That's going to be 2s to the first power, and then because it's in implicit differentiation and it doesn't that s part doesn't explicitly say what it looks like as a function with t in it, then you have to do like the derivative of the outside function was just s to the second power, that'd be 2s, times whatever the derivative s actually is with regards to t. Okay, that's it. So that looks good to me. And then the final step, you substitute in some values. Substitute in values and software. So like I said, I know that s was equal to 3 feet. I'm trying to solve for dA over dt. We established that in step 2, that dA over dt is what we're trying to solve for. And then 2, we're looking at the point where we're looking at when s is equal to 3 feet, and we're looking at the rate at which it's expanding the side is 2 feet per minute. Remember, I think it's very important to get the units right, because look what you end up with. dA over dt is equal to 2 times 3 times 2. That should be 12. Feet times feet is feet squared per minute. Does that make sense? I think it does. The rate of change of an area should have an answer that has feet squared, which is area. How fast the feet squared is changing per 1 minute. So that totally makes sense. Okay, I'm gonna go through one more before we go on to some a book problem that has to do with related rates. This is just notes to kind of get you in the mindset of thinking about rates of change, or for related rates and rates of change for like different geometric shapes and how they change, because it's really easy to remember like the formulas for those geometric shapes to begin with. Sorry, let's go ahead and back up a little bit here. Hide this and let's go down. Okay, so this one's a little bit tricky. You can try this on your own, right? And I'm gonna go through. This is gonna be the last one I go through in this packet. The rest of them have answers. The rest of them have like the rest of this packet. There's still like 4 more pages, I think, of work that you can try out and practice until you feel comfortable moving on to the book problems. Okay, but I'm not gonna go through everything. But there is a link to the key on the website if it loads up. Right here, related rates worksheet. Underneath it, there's a key to all those pages. Okay. So let's get started. Okay, so read this to yourself. Let L be the length of a rectangle whose sides. So I might actually just go on to step 3 to figure out what's going on. But let L be the length of a diagonal of a rectangle whose sides have a length of x and y. So I'm gonna just kind of work around and start at step 3. Why not? Step 3 is a rectangle with a diagonal called L. Put like a cursive L there. Side lengths of x and y. Okay. And let's go back and assume that x and y vary with time. Okay, so that tells me vary with time. That means x changes with time. That's dx over dt. Y varies with time. That's dy over dt. If f increases at a constant rate of, so I'm already picking this apart. So we're looking at an increasing rate of change for x. Dx over dt is a half a foot per second, and I'm looking at a decrease at a constant rate. So dy over dt looks like it's going to be negative 1/4 feet over seconds. And how fast is the size of the diagonal changing? Okay, so let's take a step back to step one. I got L is equal to the diagonal x is equal to a side length of a rectangle and it does give me what instance I want. So I want it to be where when I'm talking about x is equal to 3 feet, so we'll put that. We're also looking at y is equal to the you can say the other quote unquote other side length or side length of the rectangle. We're looking at the instant where that's equal to 4 feet. Step two is to kind of think of the different rates of change. I'm looking at the rate of change of x, so right there, dx over dt, and we're looking is the rate change for side length x. We're looking at the instant where that is half a foot per second. So every 1 second, this rectangle changes by 1 foot per second going this way here. So you can kind of look at like its expansion, like going that way. Like that represents dx over dt when we're looking at 1/2 foot per second. Okay, and then dy over dt is the rate of change. Again, you don't have to write all these out, but it definitely helps for you to keep track of your information for the side length of y. It's going to be, let me see if they give you that. They also want to see when it's decreasing at a constant rate of, decreasing at a constant rate of 1/4 foot, so it's going to be negative. Increasing is a positive rate of change. Decreasing means it's decreasing. It's a negative rate of change. That's 1/4 feet per second. Okay. And what we're actually looking for is how fast is the size of the diagonal changing. So we're looking at dl over dt. That's how fast the diagonal L is changing. We don't know that. That's what we're trying to solve. We're looking at the point where in our picture when x is changing at that rate and then when y is expanding out, like that represents dy over dt being equal to, or actually it's not going out. I'm sorry. Let's erase that. So y is actually going in and contracting. So let's kind of fix that. These are arrows kind of going inwards, right? So that is how dy over dt is decreasing at negative 1/4 feet per second. That's negative 1/4, okay? Then we're asking basically if what the rate of change of this guy here, dl over dt, I'm going to put it equals to a question mark. That is dl over dt. Sorry, it's really muddled here for you to see, okay? And I'm just pointing to two little arrows representing that L is maybe increasing. Maybe it's not. Who knows? Let's see. So that was step 2. We already did step 3 by drawing it in the first place. I thought it'd be easier for me to do that. You can kind of go out of order. You don't have to do any specific order here, but I'm trying to do the best so I don't confuse you. Step 4 is different. Oh, sorry. So let's go back to step 3. Let's find an equation relating the variables in step 1. So it looks like I have to go back to step 3. I'm sorry. And we got to find an equation that relates L, X, and Y. Well, it's really deceiving because you're going to think it has something to do with the area of is equal to X times Y, the area of the rectangle. But if you look closely at step 1, those weren't the variables of interest. In fact, if you look at the actual problem, it doesn't say anything about the area at all. So be careful. Okay, it's not always an area problem. In fact, we're trying to find an equation that relates L, X, and Y. Well, it did say at least that, so A is equal to XY isn't really going to help us to relate L, X, and Y. But I know it's a rectangle. If you know anything about your rectangles, rectangle should have 90 degrees. And then I know from a 90 degree, what I see with the diagonal and these two side lines X and Y, what they form is a right triangle, right? Because it's literally a triangle embedded into this rectangle that that is a right triangle because it lays within a rectangle. So I can see in that triangle, it's like saying, if I remember what the right triangle is, if you use the Pythagorean theorem, x squared plus y squared equals L squared. I can write that x squared plus y squared equals L squared. I just found an equation that relates all three of those variables. Okay, I'll just stop right there. I guess I should have mentioned that t is equal to time as well, and we do care about time in seconds here. So if you really want to write a problem with, let's see, time, you would take d over dt with all these guys. But hold on, let's just back up a second. I think it's going to make it easier if I take one more step. I want to see how L relates to just plain old L, because I'm trying to find I know I'm going to eventually try to find the dl over dt. Try to isolate L in the beginning with just L to the first power. So what you're going to do is you're going to take the square root of both sides to get rid of that square root, that squaring of L. So you can get rid of that. So you just get square root of x squared plus y squared is equal to L. Okay, and this is going to be pretty complicated, but then you're going to take the derivative of both sides with respect to t. So this is the proper equation that we're going to work with. And now we're going to actually differentiate it down here. So let's continue off with d over dt of square root of x squared plus y squared is equal to, let's see, d over dt of L. Okay. And let's go ahead and begin. So this is secretly, if you look at it, let's rewrite that one more time. That's actually x squared plus y squared to the half power. We still need to take the derivative with respect to t. And if you can, the derivative with respect to t of L is, if you take the derivative of L, the outside function, L to the first part, that's just a constant 1 times. But the derivative of the inside function is L, so that's w times d over dt. Or you can just look at this. The derivative of L with respect to t is literally just the derivative of L with respect to t. And that's not explicitly said, doesn't explicitly say anything about t being in this equation, like explicitly written out. So we just know L could be, within L could be an equation that has t in it. So the only thing we can say is the derivative of L with respect to t is literally the derivative of L with respect to t. Okay, so rewind that a few times to kind of get that logic in your head. Okay, and the derivative of this guy is, you'd have to take the 1/2 and put it in the front. 1/2 and put it in the front, x squared plus y squared. And that'd be negative 1/2 now. So you would say that's it, but you gotta take the derivative of the inside guy. So that'd be times, I would say that's 2x, okay? But if you're taking the derivative of x squared, that's 2x, but since x is not an explicit function that explicitly says anything that has to do with t, you have to kind of have some insurance and say, we're also taking the derivative of x with respect to t. Same goes for this. The derivative of y squared would be 2y times the derivative of y with respect to t. Okay, let's see if I'm missing anything. And I believe that's it. Okay. Can't go any further with that derivative. Now step 5 is to substitute in some values. Okay, so I know that x, we're looking at a point where x is equal to 3 feet, y is equal to 4 feet. Let's see what else we got. We also know that dx over dt is 1/2 foot squared. dy over dt, we're looking at the instant where these numbers are so, and then how is the diagonal changing? So let's come here and take a look here. Oh, sorry. So all of this is equal to dl over dt. So I'm going to say this again. dl over dt is equal to 1/2. Now we're substituting in values all up in here. Of x is 3 feet squared plus 4 feet squared to the negative 1/2 power times 2 times 3 feet times dx over dt, which I established as 1/2 foot per second, plus 2 times 4 foot times negative 1/4 feet per second. Now let's do some math here. So I got, let's see, so technically I got 1 over 2 times, that should be 9 feet squared, plus let's see, so that's should be times the square root of 9 feet squared plus 16 foot squared. Okay, so that's this part here, 1/2 of this guy. So that's negative 1/2 power. So that means it's 1/2 power is a square root. So that in negative means that this whole thing is going to go on the bottom of a fraction. So it's going to be 1 over 2 times the square root of 9 foot squared plus 16 foot squared times whatever's in here. So let's do some math in here. That's going to be 2 times 3 is 6 foot. 6 foot. 2 times 3 is 6 foot times 1 over 2. That's 6 times 1. That's 6. Divided by 2 is 3. So that's 3. And then like feet times feet over seconds is 3 feet squared over 1 second. Plus 2 times 4 times 1 over 4. I think that 4 times negative 1 over 4 would be negative 1 times that. So that'd be minus 2 feet squared over seconds. So it looks like we're almost approaching a negative number, but let's see how this all works out. This over here is going to be 1 over 2 times the square root of 25 feet squared times, what's 3 foot squared minus 2 foot squared? That's literally 1 foot squared over seconds. I'm sorry. Okay. And let's see if I can go further. Continue this on to the next page. So I believe, let's rewrite what I just had. I had 1 over 2 times the square root of 25 foot squared. This is dl over dt we're solving for, times 1 foot squared per second. And then if you think about this, the square root of 25 foot squared is 5 foot. So it's 1 over 2 times 5 feet times 1 foot squared per second. And then that's 1 over 10 feet times 1 foot squared over seconds. If you multiply these two together, this should be 1 times 1 is 1, and then the denominators multiply, so that's 10 times, technically that's 1 second, so that's, units stay here, feet squared. This is 10 feet times a second. And if you think about that, foot, this is feet to the first part, this is feet to the second part, that eliminates, cancels out. So your final answer should be 1 over 10 feet per second, dl over dt. Does that make sense? Because you know what? If the rate of the area was changing, that you should have feet squared changing per second. But since dl is technically just a side length, how far the side length is changing, feet per second totally do work. And it's basically saying so we know that so it's basically saying L is going to be increasing at the instant that X is equal to 3 foot. Y contracting is still 4 foot. And then we know at that exact moment that those two things are happening, that one is 3 foot and one is 4 foot, we still know that X, the side length for X is expanding at half a foot per second, and yet Y is contracting at a rate of -1.4 over feet second. I would just like to know, with all those conditions at the same time happening, what would the rate of change of the L structure be doing? And then we did, with all that math, we found out that the rate at which L would be changing at that exact same moment with those conditions is 1 over 10 feet feet squared, okay? Or I'm sorry, feet over seconds. Sorry, I'm all over the place. Okay, guys, I'm going to continue this with another part, but that was a pretty lengthy one. And I'm going to stop the video. You guys